Welcome to this lesson on equivalent expressions part 1. Please make sure you have these notes in front of you so we can begin our lesson. And my students, let's go ahead and make sure we update our table of contents. The learning objective for today says I can use algebra tiles to write equivalent expressions. So for this slide, let's go ahead and review some key concepts on the left-hand side of our notes. So given this algebraic expression right here, we're going to have to identify the terms. Now remember, the terms are separated either by plus signs or minus signs. So the terms here are, this is the first term, x to the second. Here's another term, negative 5x. Notice I said negative because I take the sign in front. Make sure you bring the sign with it. So negative 5x is another term. And the last term would be 4, or positive 4. So the terms are x to the second, negative 5x, and the last term would be 4. There are 3 terms in this algebraic expression. The next question asks, what's the constant? And notice the constant is any term that is standing alone. It does not have any variables next to it. So the only term that does not have any variables next to it is this one, which is the 4. So the 4 is the constant. The last question on this side says, what is or are the coefficients? The coefficient is the number that is being multiplied by a variable. So if you take a look at our first term right here, we have a variable. And the number that is standing next to the variable or standing in front of it, well, you don't see a number, but there's an assumed 1, or you would imply that there's a 1 standing right here. That's saying 1 times x. The 1 is the coefficient, so that is our first coefficient. It's an imaginary 1. You can't see it, but you know it's there. The second coefficient in this problem would be in the second term. Notice I have negative 5 times x. The negative 5 is the coefficient because it is being multiplied with the x, or it is the number in front of the x. So negative 5 is the second coefficient. So now let's go ahead and talk about some algebra tiles. The first algebra tile I want to talk about is this little blue square. This algebra tile represents one constant square. The little red square represents a negative 1, which is still a constant, but it's a negative number. Whenever you have a positive constant and a negative constant, you can get rid of both and make 0 pairs. Basically, 0 pairs means they make 0. So 1 plus negative 1 goes away. So if you have 0 pairs, 1 positive, 1 negative, they make 0. The next tile we have here is called a variable term tile, and this variable term tile could mean any variable. So they usually refer to it as the x tile, or the x terms. And the last tile up here is our x squared tile. So let's use these key concepts to discuss the following examples. For example 1, it says use algebra tiles to write an equivalent expression. So they're giving us this algebraic expression below that says 2f plus 4 plus f minus 6 plus f. So let's take a look at our first term. Our first term says 2f. This is a variable term, and we can use these algebra tiles to represent our variable term. So this tile represents the variable. So we can say this is going to represent f. So I drew 2 variable tiles because that represents 2f. My next term is a constant. So I'm going to use the constant positive term tile to represent 4. So I drew 4 variable tiles to represent the constant 4. Then my next term is a variable term. But remember, this f has an imaginary 1 in front of it, so our variable term is 1f. So I drew another variable tile. Our next constant says negative 6. So we're going to draw 6 of these red constant tiles. And then my last term is a variable term of f. And the coefficient would be an imaginary 1 that stands in front of it. So I drew one more variable tile. Now I can use the commutative property to switch these tiles around and place the green tiles with the green tiles and the constant tiles with the constant tiles. So this is what it looks like when I use the commutative property. The green tiles are together and now the constant tiles are together. Now I can find zero pairs. The positive and the negative cross each other out, positive and negative cross each other out, another zero pairs where the positive and negative cross out, and the last one where the positive and negative cross out. So now that I have this done, I have fully simplified my problem. So we can write the answer like this. I've got 4 variable terms, so that's going to look like this. 4f. And I've got 2 negative constant terms, which looks like this. Negative 2. You cannot combine these because this has an f and this does not. So our final answer is 4f minus 2. For example 3, it says use algebra tiles to write an equivalent expression. So for my first term, I see I have 3x to the second power. If you remember back from the key concepts, this tile right here represents x to the second power. So I need to draw 3 of them. My next term is negative 4. So I'm going to go ahead and draw 4 of these negative constant tiles. My next term is x to the second power. But you remember your coefficients, 1 in front of it. So I'm going to draw another x to the second tile. My next term is plus 6, which is a positive constant. So let's go ahead and draw little 6 constant tiles. So the next term is another variable term. Remember, there is no exponent in this one, and it has an imaginary 1 as the coefficient. So I'm going to go ahead and use this tile to represent the variable term. So I drew 1 variable tile. The next term is a positive 1. So I'm going to draw a positive constant tile, just 1. And my last term is another variable term. Remember, the exponent is 1. It's not 2. And we have a imaginary 1 in front of it. So we're going to draw another variable tile like that. So now let's use the commutative property of addition to go ahead and move all of the tiles that look alike together. So now what I can do is I can go ahead and search for some zero pairs with my constants. So this negative will cross out this positive, that's a zero pair. Here's another zero pair, and another zero pair. Okay, so let's go ahead and combine like terms, everything that we have alike. So I have 1, 2, 3, 4. I have 4 tiles that are x to the second tiles. And then I've got 1, 2 plus 2 tiles that are just regular constant tiles. Plus I've got 3 constant tiles. And you cannot combine them any further, so that would be your answer. And please know that this expression is equal to this. We just simplified it. So now it's time for a quick joke.
Oh, you're looking quite obtuse.
Don't pick on him. Not everyone is perfect like you.
I know, right?
So go ahead and pause the video and complete these got it problems, and we'll discuss the answers in class tomorrow. Notice this problem has 2 got it problems, got it problem A and got it problem B. So let's take a look at example 3. It says using the algebra tile, write an expression for a perimeter and an area. And they're giving us the algebra tile right here. That looks like a constant algebra tile. So we know that the sides of each of the constant tile, if this is a square, this is worth 1. So this side has to be worth 1, 1, and 1. If it's a perfect square, then all the sides are equal to 1. So for perimeter, I can write this formula. Perimeter is equal to side plus side plus side plus side. Whenever your PE teacher say run the perimeter, they're asking you to run around the entire field. So all the sides of the field need to be added up. So I can go ahead and plug in a 1 for each of the sides. So 1 plus 1 plus 1 plus 1. And I can combine those 1s because those are all constants. And I can get 4 as my perimeter. But make sure we put 4 units long. So around the entire perimeter, it's going to be 4 units long. The second thing we should talk about is the area. We know to find the area of a square, we can say area is equal to side times side. And we know how long one of these sides are. one side of this square is worth 1. But if this is a square, then both sides have to be equal to 1. So I can plug in 1 into my area formula. So I can do 1 times 1. So the area would be 1 unit squared. For example 2, it says using the algebra tile, write an expression for the perimeter and the area. So if we look at our algebra tile, this looks like a variable tile. And we know that this side of the variable tile is worth 1. But the other side of the variable tile, we don't know how long that is. So if we don't know how long something is, we call it x. The other side, this would have to be 1, and the other side would have to be worth x. So for a perimeter, let's go back. Perimeter would be all the sides around the shape. So perimeter is equal to side plus side plus side plus side. So now we know how long each side is. One side is worth 1. So I'll cross that out because I used it already. The other side is worth x. So I'm going to write plus x. The other side is worth 1. So let's cross it out. And the last side is also worth x. So we can cross that out. We can use the commutative property of addition to rearrange our tiles or our terms. So x plus 1 plus 1. All I do is I put the like terms together. So we can simplify this further. I've got 2x's, so I can write 2x, and I've got 2 constants, and I can write it as plus 2. We cannot go further because this term has a variable and this term doesn't. So we have to make sure we put our answer. Our perimeter is 2x plus 2 units long. For area, we know that the formula is area is equal to length times width. And we know how long one side of this rectangle is because one side is worth x. And the width of it would be 1. You can multiply x times 1, and your area would equal to 1x. But make sure you put units squared because you're dealing with area. So the expression for the area would be 1x unit squared. Example 5 says using the algebra tile, write an expression for this tile. This tile is a variable to the second power tile. So it's one of the larger squares. We don't know how long one side of these, the side of the square is, so we can call something that we don't know a variable. So I'm going to call this side x. But if this is a square, then all the sides have to be equal to x, because a perfect square has equal sides. So let's go ahead and write the perimeter for this larger square. I can write side plus side plus side plus side. And in this case, I know how long one side is. It's x. So instead of writing s's, I'm going to write x plus x plus x plus x. Notice everything that's in this equation, we all have variable terms, and they're all x. So I can combine all my variable terms. So my perimeter is equal to 4x because I've got 4 x's. And I'm just going to write units long. Now let's find the area. The area of a square area is equal to side times side, or side squared. We know how long one side is. One side is equal to x. So I can plug that x in for s, so it would be x squared. So the area could also be written like this, x times x, or x squared. They're the same exact thing, but let's make sure we write units squared because it's area. So the area inside of this tile would be worth x squared. For example 6, you want us to use these algebra tiles down here to write an expression, but notice they're using multiple algebra tiles. So let's go ahead and look at this. This is a variable to the second power square, and these are little variable squares. So let's go ahead and label the entire shape. This is worth x, this side is worth 1, 1. This side is unknown, so I call it x. This side is worth 1, 1. x, and x. So let's go ahead and find the perimeter, which is equal to side plus side plus side plus side. Basically, you're going to add up all the sides. So for my perimeter, one side, or I can just basically add up all the sides. So I can write x plus 1 plus 1. That is one side. Then I'm going to add another x for this side right here. Add another x plus 1 for this side, plus another one. And then add one more x for this side. So now using the commutative property of addition, we can go ahead and organize our x terms together and all of our constants together. So now what we can do is we can combine all of our like terms. So for perimeter, we have 4 x's, so we can write x plus x plus x plus x as 4x, because we have 4 of them. And then we can combine all of our constants as 1 plus 1 plus 1 plus 1, and we get 4. So we can't combine this further because this term has an x and this term does not, so we're going to write our perimeter as 4x plus 4 units long. That's how long it is around the entire shape. So now let's talk about area. Remember, the area means the space inside the shape. So if I redraw this shape, and I relist the sides, I can find the area or the space inside of it by multiplying side times side. So let's find the area of the big square. I would have to multiply x times x. So if you multiply x times x, you can write it like x to the second power. So the space inside is worth x to the second power. Now let's go ahead and multiply this 1 times x. So 1 times x is just worth 1x. And let's go ahead and multiply this 1 times this x, and the space inside would be worth 1x. So let's go ahead and add up all the stuff inside. So my area would be equal to x squared plus 1x plus 1x. Notice we can go ahead and combine like terms. 1x plus 1x are like terms, and it does not like terms with x squared because there's no exponent. So I can write my final answer as a, or the area, is equal to x squared plus 2x units squared. So go ahead and pause the video and complete these got it problems, and we'll discuss the answers in class tomorrow. Notice there are 2 got it problems. There's got it problem C and got it problem D on this slide. So now that we've completed this video, please go ahead and self-rate yourself and let us know how you feel. If there's any part of this video that you do not understand, please go back and watch it again. Also, come to class with some questions so we can discuss it in further detail.